Neural networks are good at recognizing patterns. They learn the patterns by adjusting the weights between the neurons in the neural network. But have you ever wondered what that learning process looks like inside the neural network? We're going to take a simple example. We have two inputs, x1 and x2, and one output. If x1 and x2 are equal, we want the output to be 0. Otherwise, we want the output to be 1. This seems like a simple pattern, but in the 1960s, when neural networks were first introduced, they weren't able to solve this particular problem. That sent neural network research into a deep freeze for about 15 years. But we know how to solve this today by setting up a simple neural network. We'll have two input nodes, x1 and x2. We'll have a hidden layer with nodes I'm calling h1 and h2, and we'll have an output layer with node O. In order to train the neural network to learn patterns, we need to set up some weights between the neurons. To calculate the values of the neurons, H1, H2, and O, we're going to take the weighted sum of the inputs to each node, add in a bias factor, and run it through an activation function. Before we set up values for the weights, the calculated output is going to be 0.5 for all of our line items. The loss is the difference between the calculated output and the desired output, that whole quantity squared. For each of our line items, the loss is 0.25 initially. So let's go and set up our neural network. We're going to have hidden node H1 with weights 1, 1, 2, 1, and a bias. Hidden node H2 with weights 1, 2, 2, 2, and the bias. And the output node with weights 1, 0, 2, 0, and the bias. In order to get started, we need to assign some initial weights. These weights are typically random values close to 0. The biases are usually set to 0 to start. Because we used random weights, it's no surprise that the calculated output looks pretty random. Let's go ahead and calculate the average loss. We're going to iterate through the neural network, adjusting the weights and biases using gradient descent and back propagation to try to get the average loss down. Let's take a look at step 1. The weights and biases have been tweaked, and the average loss is coming down, but the pattern doesn't look much better than before. Let's try step 2. Once again, the weights and biases have been adjusted, and the average loss is lower, but we're still not getting the pattern that we want. Let's keep iterating until the pattern looks better. As you can see, with each step, the weights and biases are being tweaked, and slowly the average loss is coming down. By the time we get to step 71, for the first time, line items 1 and 4 are below 0.5, while lines 2 and 3 are above 0.5. So that looks closer to the pattern. Let's keep going for 100 steps using gradient descent and back propagation to adjust the weights and biases. By the time we get to step 100, we're getting closer to the pattern we want. If we round line items 1 and 4 down, we get 0. If we round up line items 2 and 3, we get 1. Even if we iterated for 1,000 or more steps, we wouldn't get exactly 1 and 0 for our results. The learning rate controls the size of the jump between the iterative steps. It also influences how many steps you need in order to get a good result. Let's change this to 12. As you can see, the results are a little bit better. Let's change it to 20. In this case, the gradient descent algorithm became unstable because the jump between the steps was too great, and the neural network was unable to find the pattern. So let's change that back. You may recall we started with random weights. Let's see what happens if we change one of those. You can see that the pattern is the same, even though the values have changed a little. Let's see what happens if we change the pattern. The neural network is able to adjust the weights and biases to find the new one. Let's try all ones. Once again, the network can find that pattern. Let's try all zeros. By adjusting the weights and biases, the network can learn the new pattern. Let's try the opposite of what we started with. Using gradient descent with back propagation, the neural network adjusts the weights and biases to find the new pattern.